because this is the basis for all the program. If you understand electricity, it will open up a lot of things for you. You'll be able to troubleshoot correctly. You'll be able to understand what's going on, what the behavior is in this machine, what's happening. One of the questions was, I think in the quiz, was if you touch a computer with fridge and you feel a tingly feeling. What does that mean? Never happened to you?
What was that question?
No, I think it's the quiz. Okay, it's a gift. So you touch a computer case, a boiler, and you feel some kind of tingle. What is that?
Electricity.
Yeah? There's a short in the system. Something wrong with the ground. The ground is disconnected. There's a short. So you understand what's a short. You start to understand how things are behaving. Why are they behaving this way? So it's very, very important for troubleshooting. And you also understand, the more you understand, the more you feel less scared. You know what electricity goes there. If you see a transformer, you know you're going to be facing a lot of power. You know how to test small components. You know how to test a capacitor, how to test a transistor, how do you test for electricity. And again, things are becoming more and more electronic now, so it's really easier to diagnose. Okay, so recap, this is from last portion of the class. We will talk at what is the atomic theory and what is the relationship between physical electrons and electricity. So what's happening? Wire, cables. A cable has conductive material in it. What is my big cable? This is a big power cable. You understand the insulation. See it made out of wax, rubber, sheathing, and a big bundle of copper wire inside. This is underground cable. What do you think is the difference between a cable and a wire? Shane, you should know this.
Wait, I'm sorry.
What is the difference between a cable and a wire?
Well, a cable's usually a group of cables in the actual cable assembly, whether it'll have like some sort of insulation on it, whether it's like a metal or like aluminum.
Yeah. So a cable is
and like an actual wire itself is just a single conductive wire that he actually has right there.
Yeah, that's a single wire together. A cable has a bundle of cable. Like a phone, it's a phone cable, not a phone wire, because it has small little individual wires inside. The flow of electrons and how is it accomplished, how we should have a flow of electrons. Explain the electrical potential, current flow, and resistance, and how they are measured. So those three things are going to be with us till the end of this. Electrical potential. It's all on the slide, you don't have to write anything. Also known as volts. And again, we said if this were water, this will be what? Pressure. And we have flow of electrons. That's amperage. And that will be the current. And resistance. Is things that use current, things that use current and voltage. We call them loads. And if it's a water thing, it will be size of the pipe or tap. Taking some of the flow. So we talk about electrical power and how it is measured. I will explain Ohm's law. So these are the hows I'm going to go over them one by one. How do we calculate potential, current, and resistance of electric circuit using Ohm's law? I'll spend a lot of time in this portion because it's very, very important. Ohm's law can carry with you for a long, long time. And how do we calculate the power of a circuit and the BTU per hour rating for electrical resistance here? one by one. Key terms, we'll go over them. So, electrical energy. So we talked again that energy does not vanish and does not come from nothing. It always transfers from one form to another. You agree? So I ate some food this morning. I have energy. I can lift this book up. I drop it. The energy was stored in the book. It dropped. The energy transformed into sound and some friction and some heat. And it's going to go on and go on to different things. So energy does not vanish. It's always going to go from one form to another. Electrical energy is the same thing. You're going to put in some power, some mechanical power. It's going to go somewhere. Your car does the same thing. So, fossil fuel, gasoline, is energy. Your engine takes this energy, which is chemical energy, burn the fuel, produces heat in a cylinder. The heat expands the gases in the cylinder. It pushes the cylinder up and down, producing mechanical power. That mechanical power transforms from lateral or axial into rotary using the shaft. There's always a crankshaft in your car. Is that what it's called? Or a camshaft? No, not a camshaft.
Crankshaft.
There's a shaft in crankshaft. The crankshaft is like taking this vertical movement into rotary movement. This rotary movement is what we're looking for. That will go into your tire, and that will go into your alternator, which spins based on the motor spin and transform that into electrical energy. So we're taking the chemical energy in the fuel and using it for moving the car, charging the car, heating the car. So eventually using most of the energy that is in the car. However, cars are not very efficient. So the potential energy in the gasoline, how much do you think we use out of it as a percentage? And internal combustion engine, that's in your car. If it's completely working fine, how much you think of the energy from the gasoline will take into movement, heat, or charge? It's pretty pathetic.
Really,
Huh?
the liquid gas,
Yeah.
and vapor gas is different. The liquid you're gonna waste a lot more. When it's vapor, you waste
It's,
a lot.
you're gonna vaporize it anyway. But cars got more and more efficient. But as efficient as they got, how much of the energy you have stored in the gasoline are you actually using?
80%.
Yeah, I wish.
Probably 50.
I wish.
No, that's
Yeah, I'm 30%. 30% of the energy you put into gas, you buy in the gas, is used for what you want it to be. Where the rest goes? Excess heat, frictional uses, losses, stuff you actually do not use. Diesel engines are more efficient. They get up to 50. That's why in Europe they all use diesel. Even though diesel is expensive, you get 50 miles per gallon. Yeah, any regular diesel car. It has more power, and it has more probability of using energy more. Why? More compression ratio.
don't make no sense
Why not?
because diesel is hard to select.
Yes, it is. However, the engines are built to use more compression because it doesn't run as fast. So more compression means more mechanical power. You don't see a truck.
So you think less?
Yeah, you take less. Because again, you don't see a truck running with gasoline. That doesn't make sense at all. You want a lot of power. So you have big cylinders, big engines, compressing the gas into small compression ratio, and you get a lot of power out of it.
More fraction, more wear.
Yeah. So that's the mechanical power, and the concept I'm trying to get is the energy does not vanish. It's gonna go from one form to another, and we're trying to make it more and more efficient. How efficient is a jet engine? Around 95. 95% of the energy potential in the kerosene for the jet plane goes into mechanical. That's what we want. How efficient is your boiler in the house? 80, 85. That's good. Good. You can get up to 92, which means because you want heat, you don't want mechanical power. So from heat to heat, from chemical to heat, every time you change the mode of energy, you lose something. So from chemical to heat, it didn't go that far. But in a car, we're going from chemical to heat to mechanical, so there's more losses. And I can go forever about talking about mechanics, but I'm not going. So electrical energy is a form of energy, and now we are using that based on mechanical power. We are turning something, and we using that to turn a generator. Still primitive. We're still doing that. If you go to any power plant, they have a steam turbine that's lit up by diesel, by fuel oil, by charcoal, by nuclear. At the end, there is a steam turbine that is turning an engine. Same from the beginning, since the 1920s, not changed yet. So, this area of improvement. Solar panels, they're good, but they don't give you as much power. They're getting better and better. Out of the amount of sun that hits the solar panel, if the sun giving you, for example, a power of 100 watts, how much you change that solar energy into electricity as percentage? Sure, a number, low number,
10%.
10 to 15%. So still not that efficient. There are people making it more and more efficient. There are people trying to make the internal combustion engine more and more efficient. So electric energy is used to maintain desired temperature for like heating and cooling. We use that. Again, think of a transformation now. Either we use ACs or heat pumps. And again, you are changing electricity into compression, into like gases expanding and contracting, and at the end you're trying to get heat to move from one place to another. So we have to understand all that's happening in the electrical system to know what's going wrong with it. So far, what is our biggest consumption of electricity in any appliance is what component? The motor. There's a motor everywhere. There's a motor in the compressor that does a compressor is like a small car engine. You have a motor that will turn it to compress the gases back and forth, and that gives you the refrigeration power. We're done with this. Too much. We're done. So electricity, one atom is charged, and there is an electric charge in the other atom, and the charge keeps moving from one place to another. So if we have a wire here, imagine there are small little atoms of copper, and each one of them has a negative charge spinning around it, and so on. And you come in here and you give it another one. So if you push all of these out until it comes out from the end as energy, as an electric energy. Does the material loses electrons? No. You just keep it changing, giving it more energy, like a wave, like you're brushing over it. And it will go on and will turn on a motor. So, law of electric charge. Very simple. Similar charges repel, and the similar charges attract. So if you think of a magnet, when you have two positive charges, it will repel, and if you have different ones, it will attract. That is the law of charges, and that's why you always have positive and negative. Otherwise, there is no flow, and that's what enables us to keep this moving up and down. The video will make more sense. I don't want to get too much into quarterly details. So two charges, if we charge two plastic balls as positive and positive, they will repel. Negative will repel, and you want positive and negative. Why is this concept important? Because this is how we were able to produce electricity, by alternating positive and negative, and continuing by using mechanical power into magnetic power into generating electricity. And I'll show you some videos that are very mind-boggling now, to show you how this came about. Somebody realized that copper and steel have this relationship, that if steel is moving next to copper, that will generate a magnet, just by moving it. There is no magnetic attraction between steel and copper. What material has magnetic attraction? Steel, nickel, cobalt. These are the first material that can be magnetized, otherwise there is no magnet. But why does copper have this ability that if you run steel next to it at certain speed, it will generate a field. So it does generate a field, and this was the basis where we can have some kind of energy going around, and we can use this mechanical energy to generate this wave going back and forth and have electric energy. We talked about this already. Static, batteries, it's all review. So conductors cut through a magnetic field that causes displacement of electrons. For example, alternator, generator, and transformer. This concept gets a little bit too complicated, but the video will explain to you what that means. So again, think about there's a relationship between magnetism and electricity. If you have a compass that's completely magnetic and you put it close to a wire, will it move? It should move. It should move because current generates electricity. And as the current goes through a wire, it is generating a field. If I put this in the setting where it's supposed to detect voltage, nothing is touching. If I touch this to a wire here, it should beep. Enough power. Let's put it somewhere else. You hear that? Nothing's touching. What is this? Magic? There's a magnet, and this is detecting the magnet. If you were to measure the flow of electrons, I'm going to clip this on a wire, and if you see this hole here, it's basically measuring the amount of magnet caused by the flow of electrons. If I clip this into this wire, on wire, it will show me how much amperage in it. That's kind of amazing. So we will do that a lot because this is very important. So you don't even put it in here, you put it inside. It's not touching anything. And it should measure the amperage, and that's because of the magnet generated by any wire that has electricity running through it. Fascinating stuff, right? Okay. The video will explain that better. Conductor, insulator. Okay, voltage. Volts, amps, and ohms. Volts is for voltage, amperage is the flow, and ohm is the resistance. Voltage is also called potential, electrical potential difference, or electromotive force, field of force, or electric pressure. These are all interchangeable names for voltage. You will hear all these terms. What it means, it's just electrical pressure. It's a means for the flow to go from one place to another. Let's look at that. You could either have a battery, and we need a complete circuit, otherwise there's no flow. The energy, electrical energy, which is a flow of electrons, will go through the wire, turn on the lights, and come back to the negative. Once you cut this wire, nothing is flowing. It will be at the tip, unless a conductor comes in there and touch it. Generator constantly generates electricity based on spinning. So when you buy a generator for your house, either you have gas, kerosene, or diesel generator. What is it doing? It's turning something around in rotary movement, and that rotary movement is turning an alternator that generates electricity. You can substitute now by something called a Tesla wall, like a bank of battery that can do the same thing. Either you can have a battery or a generator, or you have no source of electrical energy. Electrons, they flow in an electrical circuit. By circuit means what? It has to be continuous. If the circuit is cut, there is no circuit, there is no electricity. Direct current and AC. Again, this is just an introduction, but we'll talk about that in many means. So for alternating current, you can have the flow of amperage going up and down, plus and minus. That's AC, and that is DC. It's always the same. So this is going to go between up and down, 90 volts, for example, or minus 90 volts. This will give you 90 volts all the time, either positive or negative. I should bring a battery and have you measure the amperage.
I have one.
The battery?
I have a battery, 18650.
How many volts?
It's 3.7. Should be 4.2. But it's 3.7.
Sweet. Let's test it. So, battery is AC or DC? DC. So I'm gonna set up my voltmeter on voltage and make sure it's DC. Okay, stick it. Put one in and put it out. Just make sure that you don't touch it. You can put it out in here. You touch one in and touch the other. 3.8
What else am I using? It's
volts. What if I reverse this? Put it on the other side. What do you think you're gonna get? Negative. See, this is minus sign, negative 3.8. So I have that one direction. It's gonna go for positive, negative. That's why when you reverse the polarity, you get different amperage. What if I want to put this in AC? So I'm gonna put it in AC now, and I'm gonna stick it in the outlet. 116 volts AC. And that's not gonna give you negative or positive because it's going to be alternating. So let's for experimentation. I'm gonna put it in DC and see what happens. I might get shocked. So it's getting confused. See how it's alternating? Up and down, up and down, up and down, because you can't measure. It's changing.
Those things have a fuse in them?
Yeah, but these are, they have smart logic in them, they don't get burned. But the other ones, they will get burned. The cheap one of $5, fuse, you put it wrong, it will burn. This is very good one. Amps and amperes. Position of the flow, we said like resistance, that's in ohms. And we'll talk about that again. Okay, let's do some calculation, introduction to calculation. So we say we have volts, and we have resistance, and we have current. So I'll give you the two laws we have here. First one is Ohm's law. I want you to remember this one very well. Volts, amps, and resistance. This is amp, this is volts. This is resistance. So this law, you can write it on a piece of paper and bring it to the exam. You can put it as a tattoo, I don't care. Like, if you don't remember it, it's okay. You can have a cheat sheet with you in the exam, with all the laws in it, so you don't forget them. So this law is very easy. What it means is under the potential difference of 1 volt, it will take 1 amp to go through 1 ohm resistance. So this is going to be 1 ohm, 1 amp, 1 volt. It takes a potential of 1 volt to pass a current of 1 amp through 1 ohm resistance. What does that mean to us? We really care that much. If I want to find the amperage, I'm going to divide the voltage times that resistance. But the unit has to be in amps, volts, and resistance. If I want to find the resistance, I'll divide the volts over the amps. If I want to find the volts, no. Multiply. So from top to bottom, you divide. Between the bottoms, you just multiply. We'll do a lot of exercises on those. It's very, very simple. And all you have to know is volts in the top, average and resistance in the bottom. If you switch them, that's fine. It doesn't matter. This is Ohm's law. Well, it's nature's law. Ohm just discovered. This is Ohm's law. That's what it means. So based on that, I I can calculate everything I need. If I have the, I can calculate the amperage and go find the voltage and find the resistance. Can I? All you need is those three things. You can, based on two, you can find the other one. And this is as far as it gets, and that's Ohm's law. There's another concept, which is the concept of power. Power is important because that's what you pay for at the end of the month. Did you ever look at your electricity bill? What are they charging you for?
Kilowatt hours.
Kilowatt hours. So we gotta know what is this kilowatt hour and how is it calculated and what does it mean to us. Okay, let's look at the kilowatt hour. So, if electricity is energy, what do you think power is? Let me give another example. If your gasoline is your energy, what is the power of the car based on? Yeah, horsepower. How is it? Torque or horsepower? They're both like do the same thing. But what makes a Ferrari has more power than a Corolla? Do they have the same MPG? No? Which runs through gas faster?
Bigger valves.
Bigger engine. How fast you burn this power, this gasoline is your power. So power is how fast you spend the energy. So it has a factor of time. How much does it take me to burn that gas? A Ferrari probably has 10 miles per gallon. A Corolla has 40 miles per gallon. Which has more power? A Ferrari. Is the fuel the same? The fuel is the same. Although, probably Ferrari needs the high octane. Let's just say the Ferrari was using regular. Okay, same gasoline. So power. Put it here. Remember this. Power is energy over time. Don't you get hungrier if you work out? You're spending more energy. So somebody who does not move at all, they require 2,000 calories a day. That's energy. If you move, probably you have to replenish your energy. You will get tired. You get hungrier. That's why if you go on the treadmill, it gives you the calories, and it'll give you watts. What is watt? Watt is voltage over amperage. Oh, hold on, is that true? No, voltage times amperage. If your voltage is your available potential power, energy, amperage is how much flow is there. So I have high octane, that's my voltage. How much I burn that is my amperage. So that will take me to something called the power law. Second law here, same thing. Power, voltage times amperage. It's going to be in watt. It's going to be amps. And this is going to be in volts. James Watt is the guy who realized steam power and started the steam turbine and the steam engines. And we put a measure of watts based on this. And it's very simple because, again, it's very direct unit. So watt, volts, and amps. How do you find power? Volts times amps. How do you find amperage? Power times volts, and so on. Power time over amperage. So sometimes you look at some instrument. Maybe this one has it. Look at some instrument, and it will tell you how much power is there. They should. And sometimes they try to trick you, and they don't put the watts. What do they put? They give you something called so watt. They'll say VA. What do they mean by that? V times A. So you'll see in some European instrument they want to give you the VA. But at the end we are concerned with the watts. Because at the end of the month is what you pay for. And based on each equipment, how much amperage they draw, What is the voltage in the house? You know the voltage already. What is the voltage of a household?
110.
110, 119. You know the voltage. You know the amperage. You know how much you're gonna pay for that equipment. Now I think by law they put the wattage in every appliance. So this microwave is 1500 watts. That's 1.5 watts. How much would that run me? How much is the kilowatt in Massachusetts? Come on, you pay bills. 15 cents.
That's Springfield.
And I think in all Mass, around 15
Holyoke
cents.
is different.
How much?
They got their
GKB is
own-
different too. GKB is we have our own power company.
How much?
Like,
Again, it varies how much they charge you. In the South, it takes I think it's around 10 cents. In Florida, it's 5 cents. Why Florida is 5 cents?
it's nuclear.
Huh? Nuclear. It's cheaper. Here it's expensive because it's gas. If you have coal, probably it's going to be cheaper. So, watt is VA, and what is kilo? 1,000. So kilowatt is 1,000 watt. So when you buy a light bulb that's 60 watts, that's not that much. But if you multiply the hours you run it, and you divide that, multiply that by the cost, probably a light bulb that if it's 24/7, probably it will cost you around $3,000 a month to keep that light on. Want to do a quick example? Let's do that. So if I have a light bulb, let's say 100 watt, make it simple. I'm going to turn it on and leave it on for the whole month. So 100 watt times 24 hours times 7 days a week times 4 weeks a month times $0.15 per kilowatt, and I have to divide that by 1,000 because convert from watt to kilowatt. This will give you how much this light bulb will cost you. 100 over 1,000 times 24 times 7 times 4 times 0.15. $10 a month. To get one light bulb to be on. That's a lot for one light bulb. So it adds up. So we'll do a few examples of those to see how does it add up. Again, you don't want your power bill to be this high, and if it is, you should understand why. But this is one light bulb. Again, the time and watts. We know now that watt is a measure of power. This is the power, and I want to see how much it costs. An oven runs around like how much? Probably 1.5 kilowatt, 2,000 kilowatts, and it's 220. It has its own outlet. However, how long do you use an oven? Once a week? I don't know. Huh? Yeah. So when you think about it, it's not that bad. It's how often you use it.
That's why my bill was so expensive. I used it like 4 times in a month.
See?
It was expensive, $200.
Yeah. How long do you run it for?
Not big chicken, about an hour.
So you should invest in an air fryer or something. Something quick. Yeah, an hour is a lot. So an hour, that's 15 cents. Probably like 25 cents. 4 times a week, that's $1 a week.
How many chicken breasts you gonna?
Yeah, seriously.
A whole lot.
That's $4 a week, then it adds up. So oven does cost a lot of money. However, using an electrical oven is much better than using gas. If you compare the amount of money to the safety, people will always vote for the safety, and it's not that much. But for your case, if it's an hour, how much? 4 hours a day? How many hours a week?
You used to fry it. It's healthier to do it in the oven, but it's more expensive, I think.
Not really. If you do the math, probably it's not really. If it's 1 hour a day, it's not that much. It's still not that much. We'll do the math later for fun. Just for fun. Okay. So rate in which the electrons do work is measured in watts. The formula is power equal voltage times amps. Other units you might see is 1 horsepower, which is 647 watts, and 1 watt is 3.4 BTU hour. BTU hour is our friend in HVAC. It's imperial, but we still use it because it's not gonna change. So most of the European ACs and boilers, they'll give you the energy in joules. Joules is kilowatt hour. But now you get BTU hour, so you have to have the conversion. So I will show you also why a space heater will cost you a lot of money to run. Space heater is around 1.5 watt, it's as much as your oven. And it's gonna be running for a few hours, that's a lot of money. So to convert from BTU heat to electricity, it's gonna be a lot of money. Would you think the conversion from electricity to heat is efficient or not? What do you think? Actually, it's pretty efficient. It's the most efficient way. 95% efficient. So you put in 1 watt, you gotta get 3.3 BTU hour almost. It's not that's not the problem. The problem is it's expensive. It adds up, and you're not gonna heat the room with 1 watt. It's gonna be at least 2,000 watts. So it's a lot. I will do some math to just understand, get a concept of why do things cost so much money, and what does it matter to cut power here and there. Electric power and energy, we talked about that. It's measured in watts hour or kilowatt hours because they don't want to give you a huge number, so they put it in kilowatts. And this is the same power law we have here. It gets a little bit complicated, don't worry about that, they give you all the variation. So if you want, I here is the amperage, the book referred to the current as I instead of A. So I is E over R, which is voltage over R, and the same thing here, it's just a variation. And there's another variation that's really complicated that I don't like. This one is how do you go from power to resistance. It's kind of like creepy to see squares and stuff, so don't worry about that. We will just use those two. And I'll show you how you can use those two and not have to worry about that. Let's do a couple of examples. If the voltage is 120 volts and the resistance is 0.5 ohms, what is the current? What are we gonna do? So I'm gonna go to my Ohm's law. I need the current, right? So I need the current, then cover the current, and that's volts over resistance, right? So easy way is amperage equal volts over resistance equal 120 over 0.5.
Are you looking for the watts?
60.
No,
240.
240.
Yeah, 240.
240 amps. That's pretty huge. No equipment will do that. This is very small. This is really unrealistic. But just to give you a simple numerical example. 240 amps. If the voltage is 220 and the resistance is 0.5, what will be the current? Same thing. Current. Voltage over R. 240. 0.5. 480 amps. Nothing in the real world consumes much. I don't think there is a cable that can take that much amperage. And when amperage goes through a wire, it does two things.
440.
Huh?
440.
440? Oh yeah. Are you sure? Oh yeah, it's 420. So when current goes through a wire, it does two things to the wire. What is the first thing? Heat. Second thing? Huh?
Magnetic field.
Magnetic field. These two things are going to be very good indication of what current is going through. If the voltage is 110, the current is 5 amps. What is the resistance? So this time, I'm looking for the resistance. So voltage over amperage. What is that? 22? Ohms. Easy.
22.
So, not that complicated, right? Doesn't get complicated. We'll keep it this simple. More example. If the voltage is 120 and the resistance is 0.5 ohms, and the current is 240 amps, what is the power?
Do you need the formula for that one already? Power.
So, to find the power, I need the voltage and the amps. So, I don't even need the resistance. So, power equal voltage times amperage equal 120 times 240 amps. Again, that's really not realistic. What do you get?
28,800.
Watts.
28800.
If I want to convert that into kilowatt, it's 28.8 kilowatt. I just divide by 1,000. If the voltage is 220 and the resistance 5, the current is 440. What is the power? 220 times 44. If the voltage and the amps and the resistance, what is the power? Voltage and current. Again, in these examples, because you need the power, you don't need the resistance, or you need the voltage and the amperage. Sometimes, what if I give you the voltage and the resistance? Can you find the?
968.
Yeah. Let's do an example. I'm gonna do an abrupt example here. Voltage 110 volts. Resistance 200 ohms. This is simple for ohms. What is the power? So power will equal volts times amps, correct?
You don't have the amps.
I don't have the amps. So amps equal volts times resistance. I have the volts, 110 over the resistance, 200 ohms. That equals, calculator, do the number in here. Now I have the amps, right? So 110 times 0.55. I got 60.5 watts. Good? Very straightforward. Do not complicate things. Two laws. Having two things is enough to find the others. Four of those. I think there will be a homework if you have any questions about that. It doesn't get more complicated than this.
Use the ohms calculator that they have online.
Huh?
You always use the ohms calculator that they have online.
Yeah, you can use your own calculator now.
Yeah.
So this will be very handy. Okay. I want to watch the video. At least 2 segments of it. Very, very interesting. All right, yeah.